All right, well, it's time to get started. Got an exam on Monday covering chapters 4 and 5. So, plan today is to review chapters 4 and 5 and answer any questions that y'all may still have. So, who's got a question? Chapters 4 and 5. All right, then I'll ask y'all a question. What are Newton's laws of motion? How many are there? 3 of them. Okay, what's the first one? Very good. And what's the short name for that one? Excellent. An object in motion will remain in motion and an object at rest will remain at rest unless acted upon by an outside force. A simpler statement of the same thing, a simpler way of saying the same thing is that the natural state of an object in this universe is to be unaccelerated. If it's moving, it will continue to move in a straight line. If it's not moving, it will continue to not move. What does this word right here? Outside. It says, unless acted upon by an outside force. Okay, outside of what? Its point of view. That's actually exactly correct. What's the terminology we use to describe that point of view? It's reference frame. More specifically, an inertial reference frame. And an inertial reference frame is what? Think of the cup of coffee sitting on your dashboard. An inertial reference frame is a frame of reference that is unaccelerated. That's the law of inertia. The natural state in this universe is to be unaccelerated. What's the second law? F equals ma. And F and A are both vectors. So the more accurate statement of Newton's second law is the vector sum of the forces is equal to the mass of the object times its net acceleration. In order to understand and use Newton's second law, we have to know what does mass mean? What is mass? And what is inertia? We don't know. I mean, that's the blunt answer. We don't know what inertia is. We can't describe it to you or tell you how to produce it. All we know is that all matter has inertia. And mass is what we came up with to define and to quantify matter. All matter has mass. And the more matter you have, the more mass that matter has, the more inertia that matter has, or that object. So, what are the units of mass? If it's science, we have to be able to measure it. When we measure mass, what are the units that we're looking for? What units are we measuring it in? Kilograms. Units of mass. Kilograms. Now that is, of course, in the MKS system of SI units. Now how's that for a mouthful of letters? SI, MKS, CGS. What do all those letters stand for? It's standard crap, yeah. That's no. You're getting there. Meters, kilograms, and seconds. That is what MKS stands for. CGS stands for centimeters, grams, and seconds. Centimeters, grams, and seconds. SI stands for Système International. Right? In general, anytime you have a word that ends with T-I-O-N, if you just say it's snooty, you've just spoken French. Pretty much every English word that ends with T-I-O-N is the French. It's the same in French, the same word in French. You just say it's snootier. Système International is the standard. It's the international standard units of measure. We use MKS in physics. We use MKS in astronomy. What are a couple of examples where you might run into CGS? One example is right next door. In Dr. Sullivan's class, what does he teach? Chemistry. The other one would be biology. Biology and chemistry tend to use CGS because they tend to work with smaller quantities. Okay, that's first and second laws of motion. What is Newton's third law of motion? Every action has an equal and opposite reaction. Boom. Who can tell me the first thing that brings into our studies? What's the first thing we learned from the Newton's third law? The normal force. Excellent. The normal force. From his second law, we know that cup is at rest. It will stay at rest as long as the sum of the forces acting upon it are summed to a net zero. We also know that one force it's experiencing right now is gravity. The mass times the acceleration due to gravity is producing a force pushing it down towards the center of the earth. The table then is exerting an equal and opposite force to stop that from happening. And so the sum of, in this case, the sum of the force due to gravity plus the normal force equals zero, because by Newton's third law, they are equal and opposite. Now, if I pushed down on that cup with enough force, what would happen? Well, or I would tip the table. I might tip the table over. Okay, but in order for it to move, I would have to exert enough force to overcome whatever mechanism is exerting the normal force against it. Okay? What if that cup were sitting on an inclined plane? It's still experiencing the force due to gravity. Mass times g, mg. What's the normal force now? The normal force is whatever force the table is exerting against the cup. And the cup is exerting an equal and opposite force against it. But that force is a component of the force of gravity. We'll draw it right here. Now, if this is the force due to gravity, mass times gravity, what are the components of that force vector that are acting upon the cup? If this is angle theta, then the force that the cup is exerting on the inclined plane is the perpendicular component of that vector, which would be Mass times gravity times the cosine of the angle theta. That's the force of the cup on the table, on the inclined plane. Okay? That means the normal force that the inclined plane is exerting on the cup is the opposite, equal and opposite of that force. Okay? But what happened to the rest of that vector, that gravity vector? Because the gravity vector is is the real force involved here. This is the real force. The gravity vector is pulling it down. This force exerted, the cup is exerting on the inclined plane is only part of that gravity vector. The rest of that gravity vector is this. Mass times gravity times this, not cosine, times the sine of the angle theta. And it is pushing like so. That is the force that is accelerating the cup down the plane. But what if the cup isn't moving? Because we can see that if I lift this table and I incline it, that cup does not start sliding. Why not? Because of the force due to friction. We know that the total acceleration is going to equal the net sum of all of the forces. If the cup isn't sliding, then all of the forces have to equal 0. And so this force of acceleration is equal to minus the force of static friction. Right? The force due to static friction is what? Anybody? It's the normal force times the coefficient of static friction, mu sub s. Now, if we incline that plane further and further, at some critical angle, that cup will start to slide. It will start to slide when this force, mg sine theta, exceeds mu sub s times the normal force. And look what happens. As you incline that table further, two things happen. The sine theta, the sine of the angle gets bigger as the closer you go from 0 degrees to pi over 2 degrees, or to 90 degrees. The sine function, the sine force vector starts getting bigger and bigger, and the normal force vector starts getting smaller and smaller, until this condition becomes true. And as soon as that's true, the cup starts to slide. At that point, what is the force of friction once the cup starts to slide? What's the other kind of friction? Kinetic friction. And that's equal to the mu sub k, the coefficient of kinetic friction, times the normal force. Now, what's the one thing we always know that we know is always true about the relationship between the coefficients of kinetic friction and static friction? Say again? Static is always greater. That means once you exceed the maximum coefficient of static friction, once you exceed the maximum force of friction, of static friction, and the object starts to slide, it's going to accelerate until its force of friction, force of kinetic friction, it completely offsets the accelerating force. Okay, the force of the sine component, the sine theta component of mass times gravity. Once the two are equal and opposite, the cup will continue to slide, but at a constant uniform speed. It will no longer accelerate. What happens if I take a cup, or take this? You know what, while I'm at this, everybody sign in there, pass that around. What happens when I take this stapler and I slide it down the table? If I give it a push and start it sliding, will it just keep going until it hits Devin? Graham? Ooh, I'm halfway there. Halfway there, and we're already over halfway through the semester. See, I told you I wouldn't remember your names by the end of it. Will it continue, or will it get partway and stop? Why? Because the sum of the forces is mass times acceleration. And as long as it's moving, it is experiencing a force due to kinetic friction. Now, once I give it a push, I accelerate it in that direction. I give it some initial velocity, but if I'm not continually pushing it and increasing the force in that direction, I give it an initial velocity. Once I let go, I'm no longer accelerating it in that direction. It's no longer experiencing a force to move it in that direction. It only has its initial velocity and is undergoing a net acceleration of minus u sub k times its normal force, which will accelerate it until it stops, at which point it will now be subject not to kinetic friction anymore, but to static friction. So, just in case I need to say this out loud, because some of you may not, I don't know, you should understand, you should know this by now, but just in case I'm going to say it out loud, make sure you have your kinematic equations either committed to memory or written down on your index card. You will always need to be ready to use your kinematic equations. Okay? If this were a problem on the test, given an initial velocity, an object starts to slide across a table and it experiences, this is the coefficient of kinetic friction between the object and the table. How far will it travel before it stops? How long will it take for it to stop? These are all questions that you would answer with one or the other kinematic equation. Yep. What is meant by the phrase unbalanced force? Somebody, anybody? You got a guess? You? The unbalanced force. Going back to Newton's second law of motion, the vector sum of the forces is equal to the mass times whatever acceleration it experiences. The more mass you have, the more force you need to produce a given amount of acceleration. Or, stated differently, the more mass you have, the less acceleration a given force will produce. The unbalanced force is whatever non-zero force remains after all of the other forces have added together. In this case, as long as the sine, the gravity times sine of the angle is less than the maximum force due to static friction, the vector sum of all the forces, the cosine component of gravity and the normal force will be equal and opposite, and the sine component of gravity and the force due to static friction will be equal and opposite. They will all sum to zero. There will be zero unbalanced force, and the cup will remain at rest. It will remain still. It will not start to move. But once the angle increases to the point that the accelerating force parallel to the plane is greater than the maximum static force of friction, then that extra bit of accelerating force, that non-zero component of the sum of the forces, is the unbalanced force. Okay? So, if you've got a box hanging from a rope over a pulley and a counterweight here, and the two are completely equal, the two are equal and opposite, then the tension here the tension in that rope, it all sums to zero. As long as everything's equal and opposite, it sums to zero. The two just hang there. The two weights just hang off of the pulley. They don't accelerate one way or another. If you then hang an extra weight on this one, now the vector sum is no longer zero. And that extra non-zero component of the vector sum of the forces is the unbalanced force. It's what will produce the acceleration. So, remember that. The unbalanced force is the non-zero component of the vector sum of all the forces. Okay? Or you could state it as simply as the unbalanced force is the vector sum of all of the forces acting upon the object. And if they all sum to zero, then the unbalanced force is zero, and the net acceleration is zero. All right? Do we have any questions? Any questions from this? Because I'm about to move on from chapter 4 to chapter 5. What is the net force? What is the name of the net force that produces circular motion? Centripetal force. What does centripetal mean, or centripetal? What does the word literally mean? Center pointing. Thank you. Excellent. Center pointing force. We mathematically analyzed the force of an object moving in a circular path and came up with a mathematical expression to describe the center pointing force or centripetal force that produces circular motion. We then came into the lab and did experiments to confirm that that was an accurate mathematical expression of centripetal force. Who can tell me what that mathematical expression was? Force centripetal. It's a force. What are the units of force? What's the unit of force? A Newton, which is one kilogram meter per second squared. We know from Newton's laws of motion and which law? His second law in particular, that force is always equal to mass times acceleration. So we know the first thing in our expression of centripetal acceleration is the mass of whatever it is that's being moved in a circle. That leaves the acceleration component. And from the definition of a Newton, we know that acceleration units are meters per second squared. So, whatever the centripetal acceleration component is, has to have units of meters per second squared. We analyzed it and found that it was, anybody? Anybody remember the expression of centripetal acceleration? Well, mass times acceleration, that's Newton's second law. When the acceleration is center-pointing, is centripetal? V squared over R. Thank you. V is velocity, which is meters per second. It's squared, so we've got meters squared per second squared. And we divide by the radius of curvature of the motion, which means we're dividing by meters, which cancels out one of the meters squared, leaving meters per second squared, which is the unit of acceleration. Centripetal acceleration is V squared over R. Centripetal force, mass times V squared over R. Does everybody get that? Okay, it's very important, not only in terms of centripetal forces and accelerations, but in general. With regard to kinematics in general, it's important to remember the difference between force and acceleration. So there's a difference between mass times acceleration and just acceleration. If you were asked for the mathematical expression of centripetal acceleration, you don't write mass times v squared over r. You simply write just v squared over r equals centripetal acceleration. Now, did everybody do the homework from chapter 5? Have you all done it and turned it in? Do you have any questions about it? Seven? Which one is that? 142? 132? A car drives straight down toward the bottom of a valley and up the other side on a road whose bottom has a radius of curvature of 115 meters. Okay, so we're coming down and back up, and this radius of curvature is 115 meters. At the very bottom, the normal force on the driver is twice his weight. So it's actually minus 2 mg. So down at the bottom, the force that the car is exerting on the road is 2 mg. Well, in particular, the driver as well. Now it's asking, what is the speed of the car? Well, the normal force at the very bottom, we know what about it? Anywhere in the curved part of this, the normal force is equal to the centripetal force. So we have 2 mg is equal to mv squared over r. Get rid of the masses, they don't matter. So we've got 2g, multiply both sides by r, and that's equal to v squared, so v is going to be the square root of 2 times g times r, where g is 9.8 meters per second squared and r is 115. Now, what does that give us? 2 times 9.8 times 115 equals 2254. Take the square root, and we end up with 47.5 meters per second. And this is an odd-numbered problem, right? Well, let's check the back of the book and see if we got right. We got it right. Oh, chapter 5, 7. Nope, it says 34 meters per second. Why is it giving me 34 meters per second? Somebody, anybody? Say again? Well, Yeah, exactly. How do you leave out the 2? What he's noting is that if you leave out that 2, then you get the right answer. So the question is, why would you leave out the 2? Say again? Okay. Well, the danger here is oversimplifying. What you want to do is you always want to draw your full vector diagram. What are all of the forces acting on this car? What is the weight? What is the force acting on this car here? Force pushing down on the car. Say again? The force pushing down is just mg, not 2 mg. Does everyone understand that? Now, the car is experiencing 2 mg pushing up. But the force pushing down is still only mg. What if the force pushing down were 2 mg? We know that the force pushing up, the normal force, is twice that. What if the downward force was also equal to 2 mg? What would the net acceleration of the car be? If the normal force pushing up is 2 mg and the force pushing down is 2 mg, by Newton's second law, force equals mass times acceleration, or the sum of the forces equals mass times acceleration. If both are 2 mg, what is the total acceleration? 0. The total centripetal acceleration is 0. The total linear acceleration is 0. The total acceleration of the car is 0. Which means it would not continue in a curved path. It would have to continue straight on, tunneling through the road in a straight line. It's not going to do that. Okay? That's why it's always important to think through the physics of what's actually happening and draw a vector diagram of all of the forces. The gravity pulling down on that car is not changed. The G, it's on the surface of the earth, G is 9.8 meters per second squared. The mass of the car doesn't change. It stays the same no matter what the acceleration it's experiencing. mg doesn't change just because it's going in a curve, in a circular path. Say again? The car, the normal force right here pushing up on the car is 2 mg. Exactly. The sum of the forces now are, if up is positive, down is negative, it's minus mg plus 2 mg equals 1 positive mg. Okay, so now that is the net centripetal force. this 2mg is actually equal to the force normal due to gravity plus the force centripetal. Does everybody understand that? So now, this is no longer true. It's 1 mg is equal to the centripetal force, which is v squared over r. You cancel out the masses. You end up with r times g equals v squared, and the square root of rg is equal to its velocity, which should work out to 34 meters per second. Is that what anyone gets? Everyone gets? Now, the big question, does everyone see the trap of that you could fall into there by not thinking it through? And this is the way it works. This is the nature of doing this kind of stuff. You have to think it through. Don't be too quick. Think through all of the forces involved and look for the vector sum. Whether you're dealing with centripetal motion of a car at the bottom of a hill or the piano being lifted by the mover. That was a mistake that came and got a couple of y'all on that homework assignment about the guy lifting the boxes with the pulley. Y'all apparently went back and saw where the movers were raising a piano, but they were using a double pulley, where they had a pulley at the top and a second pulley at the bottom, so the tension in the rope lifting it was actually divided between the two. We're going to be looking at work and power next week. We're going to start on it next week after the exam, and hopefully we'll get more into, how inclined planes and blocks and tackles and how they save energy, how they help you do things that you couldn't otherwise do. That block and tackle example is a perfect example. By using that second pulley, you divide the tension. Now you double the distance you have to pull the rope, but you cut the force you need to do it in half. So in order to lift a 500-pound piano, you only have to pull 250 pounds on a rope. Assuming that there's such a thing as a 500-pound piano, I have no idea what they weigh. I know they're heavy. I've never actually weighed one. Any other questions? Well, one more thing then that you definitely need to know. That is Newton's universal gravitation law. Started to end that one too soon. Who can tell me the mathematical expression here? Somebody? Not m squared, though. No, it's m1 times m2. They're two separate masses. Gravity, the force of gravity exists between two separate masses or two separate objects. Now, on Earth, the force due to gravity is mass times gravity. Little g. Okay? I want y'all make notes of this. Do not confuse big G for little g. Uppercase G is Newton's coefficient of universal gravitational constant. Whatever you want. Not a coefficient, it's his universal gravitational constant. And it is 6.67 times 10 to the minus 11. Is that right? Somebody look that up and make sure. And give me the units. Newtons meters squared per second squared, something like that. Newton meters squared per second squared. Is that right? Kilogram squared. Is that right now? Newton meter squared per kilogram squared? All right. Little g is 9.8 meters per second squared. It is the acceleration due to gravity on the surface of the Earth. If you set the force due to gravity on a mass 1 we'll call it, equal to mass 1 times the gravity, the little g, set that equal to the force, to Newton's universal law of gravitation, g times m1, m2 divided by r squared. The m1's cancel and we find that little g is equal to the universal gravitation constant times the mass of the Earth divided by the radius of the Earth squared. And if you look inside the front cover is inside front cover, the mass of the Earth 5.98 times 10 to the 24 kilograms. Break out your calculators. Let's do the calculation real quick. The mass of the Earth on the inside cover of your book. 5.98 times 10 to the 24 kilograms. Divide that by the radius of the Earth squared, which according to the inside cover of your book is 6.38 times 10 to the 3. So divide that by 6.38 times 10 to the 3 squared, and that gives you 1.469 and some other digits times 10 to the power of 17. And if we divide that, if we then multiply that by the universal constant, g of 6.67 times 10 to the minus 11, and I just and I get 9.79, and I'm off by a bunch of orders of magnitude here, so somewhere I lost some coefficients. I didn't leave anything out of that equation, did I? All right, well, that's pretty much the end of the class, so does anyone have any questions before y'all leave? Chapters 4 and 5, Exam is on Monday. Has everyone signed in? 6 out there, 1, 2, 3, 4, 5, 6 on here. All right. See y'all Monday. Have a good weekend.